Everybody, we're going to do exponential and logarithmic functions today. Looking at exponential equations, logarithmic equations, and some compound interest. Exponential equations. So an exponential equation is one where the variable occurs in the exponent. So exponential equation, exponent. The variable x represents a difficulty because it is in the exponent. So to deal with this difficulty, we can take the logarithm of each side and then use the laws of logarithms to bring the x down from the exponent. So here we have 2 to the x equals 7. So if we take the natural log of both sides, and then we're going to bring x down using the property of law 3, and you don't have to tell me which property it is. And then you can solve for x. So we have the natural log of 7 over the natural log of 2. Use your calculator, and then you'll get your answer. Recall that law 3 of the law of logarithms says that if you have log base a of a to the c, you can bring c down to the front. So here's the guidelines for solving exponential equations. First, you want to isolate the exponential expression on one side of the equation. Take the logarithm on each side, then use the laws of logarithms to bring down the exponents and solve for the variable. So here we go. We have find the solution of 3 to the x plus 2 equals 7, rounded to the 6 decimal places. We're going to take the common log of each side using law 3. And now we can bring the exponent down to the front. Divide both sides of by log 3. And finally subtract 2 from both sides. And then we can solve to get our estimated answer of negative 0.228756. So we can check our answer by putting it back into the equation. Let's take a look at solving the equation e to the 2x, e to the x, and minus 6. Now, I want you to look at the top. Remember, these are exponents. So we have 2x, x, and no x, okay? So let's take a look at, let's take a look at how to solve that. We're going to isolate the exponential terms. We're going to factor it. How do we factor this? Well, we can take e to the x and separate it from the 2. So now we have e to the x raised to the second power. And this actually factors to ex minus 3 and e to the x plus 2. Now we can set each one of those equal to 0 and solve for e to the x. The equation e to the x equals 3. We'll then take the natural log of both sides, which they kind of skip this step, but we can show it here. If we take the natural log of x, e to the x, and then we're going to stick the natural log here in the front. Well, remember the natural log of e, those two are inverses of each other, so that'll leave you just with x. So x equals natural log of 3. Same with the other side. We're going to take the natural log of both sides, natural log here, natural log here, and remember we're taking it of the whole thing, negative 2. So we want to make sure we use parentheses there. And now we see that, well, we could have recognized this first. I didn't catch it. But here we have e to the x equaling -2, and that doesn't have any solution because we know that e to the x has to be bigger than 0. So this one just has no solution. So again, kind of like when you have the absolute value of something equaling a negative and there's no solution, knowing that the range of e to the x has to be bigger than 0, you'll know that this does not exist either. So ln of 3 is 1.0986 is the only solution. Okay, let's look at some logarithmic equations. So we have logarithmic equation is one in which the log appears on both sides. So last time we started with the exponent, this time we're starting with the log. So if we want to solve for x, we write the equation in exponential form. So we want to take 2 to the 5th equals x plus 2. We know 2 to the 5th is 32, then 32 minus 2 will equal 30. Another way of looking at the first step is to raise the base 2 to each side of the equation and do it that way. I think this way is much more complicated than the other way, but that might be easy for you to understand. So the guide is similar here. We want to isolate the logarithmic terms on one side of the equation. You might first need to combine the logarithmic terms, write the equation in exponential form, and then solve for the variable. So solve each equation. Here we have the natural log of x equals 8, and then we have log base 2 of 25 minus x equals 3. Now remember, natural log is the log base e. So if I have natural log of x equals 8, that means e to the 8 equals x, and I can put that in my calculator and get my estimate. For b, if I have the natural log of x equals 8, oh, here's another way actually, not for b, this is for the same one. We want to raise both sides to the base e, and then e, ln x are inverses of each other, so it's just x. So either way, which makes more sense to you. Now look at the second one. We're going to rewrite the equation in exponential form. So we have 25 minus x equals 2 to the third. 2 to the third is 8. Subtract 25 from both sides. And then after you do that, we're going to divide by negative, and we have 17. So we're going to check our answer. Whoop. Okay, so now we're going to look at, again, initial intensity of light. So I for intensity of light after going through a material, and x is the distance in feet that the light travels in the material. So we have a law called Beer-Lambert law. Okay, so the Beer-Lambert law is -1 over k ln I over I sub 0 equals x, where k is the constant depending on the type of material. And this is a transparency of a lake. So for the equation, we have our I, we have a certain lake that is 0.025. The light intensity for the lumens is 14. And we're going to find the light intensity at a depth of 20 feet. But first, we're going to isolate the logarithmic term, dividing both sides by negative, or multiplying both sides by negative k. We're going to write it in exponential form, so e to the negative kx would equal I over I sub 0, and multiply both sides by I sub 0, so we see we need the initial intensity times e to the negative kx. So for find I using the formula from part A, we know we have 14 for the initial, negative 0, or actually 0.025, and then 20. And we're going to put it in our calculator and get 8.49. The light intensity at a depth of 20 feet is about 8.5 lumens. Next, we're going to take a look at compound interest. You might hear my little grandson whispering in the background. If we have a principal P that's invested at an interest rate R for a period of 10 years, then the amount A of investment is going to be given by this formula. We looked at this before. And then here we have our compound interest continuous formula. So if we have $5,000 and we're going to invest it at an interest rate of 5%, first time required. Okay, so again, sum of $5,000 invested at an interest rate of 5%. We're going to look at semi-annually and continuously. So this is good because I want to look at two different ways. Think about what you think would be the best way to invest, whether it's semi-annually or continuously. So first, N is going to be 2 when it's semi-annually because it's twice a year. We're going to plug everything into our formula. Divide both sides by 5,000. Take the log of each side. And then, of course, law 3 brings down the exponent. And we're going to solve for t. Put it in our calculator, and we see that we get 14.04. So the money will double in 14.04 years. Now we can use a formula for compounded continuously. Take a look at the same thing. Divide by 5,000. Take the natural log of both sides. Solve for t. And then put it in your calculator. And you can see that if it's compounded continuously, it'll double in a shorter amount of time, 13.86 years.